Have you heard about ICE? Initial, change, and equilibrium. This is the problem of ICE. So it's a limiting agent means you put A and B in the reaction mixtures, and which one is put in a limited amount. That's a limiting agent, right? So which is shown up here. So now this one start with reading the problem. Okay, I see the oxygen here. I see the hydrogen here. They're gonna react. So I guess a hydrogen react with an oxygen. They're gonna make H2O. All right. So I'm gonna write it. And I'll finish up the stoichiometry. So I'll probably put like this. Right. So you need 2 moles of H2, 1 mole of O2 to make H2O, and they give out this grams. Right. They just want you to have you to calculate into a number of moles. So all you gotta do is, okay, I write this equation down, and the first thing is, as I show here, I just calculate the number of moles, and which one, how many moles. This one is, let's just say I have a 6 and I have a 2, right? Well, I have a 3 and I have a something. So you got the numbers, right? And then you look at that, and then I remember writing this, I need 1 versus 2 ratio, right? And look at that, which one is given 2. So let's say 2.7, if you multiply this by 2, is it bigger than that or smaller than that? It is smaller than that, okay? If you multiply this by 2, you'll get 5.46, right? And that is smaller than that, means you have more than what you needed as far as oxygen is concerned. So therefore, oxygen is a limiting agent. So that's what I figured it out just simply by converting mass to the moles. And then so step 2 is this, you do the ICE. So I write down the equation, I write ICE, and I write down 6.29, 2.73, and no water. Okay? So that's what I wrote. And then I say, okay, oxygen must be used up completely, so that's gone. And to use that up, you need to use this amount. And when you generate same number of moles as you consumed on hydrogen, so that's a plus 5.46. So then you add it up, and then this one you ended up leaving out 0.83 hydrogen, no oxygen, and then the water as your gas. This is all gas. Okay, so this is all gas. All right, and then so I got so far. Okay, the reaction is complete means something that is completely used. And then what is a total pressure? They ask you. Okay. And then what was given? Okay, the temperature is given, so I can make this one to the temperature. I can make this one to the volume. And then they say, what is a pressure here? Okay, so then what you do is, here, this is a number of moles of H2. This is a number of O2. This is a number of moles of H2O. Right? And the total pressure is, let's say P must be a volume N total RT. Right? Okay. So I guess if you look at that, going back to this, what's my N total? N total means everything. H2, O2, H2O, right? You put everything together. So here 0.8 plus and 0 plus 5.46. And you put that numbers and you put that NT value, and R 0.8.3, and then the temperature. So you put all these numbers. So you can get this total pressure, and that number is actually has to be, you can directly calculate it as 18.718. So this is a total pressure. And have you heard about partial pressure? Partial pressure. Partial pressure is nothing but combination of each individual component's pressure to the total pressure. So this wall, okay, this wall experiences 1 atmospheric pressure. There's a nitrogen constantly bouncing in, and there's an oxygen constantly bouncing. So each one of them constantly contribute to the same pressure rise. So it's the same equation. It looks like kind of funny, but pressure of H2O is nothing but NH2O RT over V. Pressure of O2 NO2 RT V. Partial pressure of hydrogen NH2T. And I know this is already 0, so this one is 0 here already. But I can plug the same the way. I can get my N2 values up there, which is 0.8, plug it in and calculate the numbers. This is what they did. For water, and this is for the hydrogen, this is what they did. And as far as the oxygen is concerned, this is 0. If you add them together, that's the total pressure. If you just calculate NT in the beginning, you'll get the number right away because NT is just 5.46 plus 0.8. This one seemingly the very simple equation, but it has a lot of implication because it does not, whatever the collision that's gas molecule happening to the wall to kind of make the pressures, one hydrogen bouncing, one oxygen bouncing, one water molecule bouncing is same equally counting. This is the one that if you're taking the physical chemistry, you'll learn that in more details from the kinetic theory of gases in your third year of chemistry.